Hey guys, welcome back to General Chemistry. Today we're going to continue talking about dimensional analysis as applied to chemistry. This video will be introducing molar mass. So in the last video we talked about how to get from atoms to moles or moles to atoms. But here's the problem. You walk into a general chemistry laboratory. We don't have any way of counting individual atoms. We don't have any instrument where I put my sample on there and it says, this is how many moles you have. So how are we gonna do some sort of analysis while we're in the lab? So let's think about the things that we can measure in the lab. So here we've got a pH meter. We'll talk more about that in general chemistry too. Here we've got some graduated cylinders, so they measure volume. There'll be a connection that we make with volume later on. Today, we're going to focus in on this one. So this is our scale, or our balance, and it's going to measure things in mass, the unit of grams, right? So it would kind of be handy if we had a connection between like grams and maybe moles. That would be a helpful connection to have. I can easily walk into a lab and put stuff down onto a scale. How can I calculate moles from that? So the way that we're going to do that is through something called molar mass. The actual definition of this sounds really complicated, so I'm going to read it and I'm going to break it down. So the atomic mass in AMU of an element is numerically equal to the mass in grams of 1 mole of that element. So the element I'm going to use as an example is sodium, chemical symbol Na. So what this is saying, that if I would walk over to the scale in the lab and I were to weigh out 22.9897 grams, where did I get that random 22.9897 grams? Well, that's the atomic mass of sodium. So I looked at the periodic table, little number on the bottom, said 22.9897. That number, the atomic mass, is equal to the mass of 1 mole of that substance. So I walk over to my scale, I weigh out 22.9897 grams of sodium. I have weighed out 1 mole of sodium. Pull out a periodic table. If I wanted to weigh out 1 mole of carbon, how many grams would I weigh out? Okay. So looking at the periodic table, we find carbon, 6th element. Little number at the bottom is 12.011. So if I want to weigh out 1 mole of carbon, I would walk to the scale and weigh out 12.011 grams. Lastly, if I wanted to weigh out 1 mole of copper. So copper is the 29th element. If I wanted to weigh out 1 mole of copper, walk over to the scale and I would weigh out 63.546 grams of copper. So that's what molar mass is. It's connecting the grams equaling 1 mole of that substance. Here's a periodic table. So there's the carbon, 12.011, copper, the 63.546. Since we have it, let's do another one. If I wanted to weigh out 1 mole of magnesium, I would weigh out 24.305 grams of magnesium. So that little number on the bottom is the number that I'm looking at. Guess what we have now? We've got an equality. So our new equality tells us that 1 mole is X number of grams. We've never had an equality that had an X in it before, have we? So why is there an X? Little wrinkle. It depends on what we're trying to determine. What is the problem asking us about? What element are we looking at? So if we were looking at sodium, that X would be 22.990. If we were looking at krypton, that X would be 84.798. So this number right here depends on whatever the problem is asking us. It's specific to that problem. With equalities come conversion factors. So we can use this to go from grams. We weigh out a number of grams in the lab, and that can tell us how many moles. Or I could have a sample that's a certain number of moles and try to figure out, well, how many grams is that? So we can go back and forth. So let's look at an example. According to the national guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 7.4 grams. What is the estimated average requirement of potassium in moles? Okay. So what are we going to do for every unit conversion problem that has ever existed? Write down the information that's given, the first measurement. So I'm going to write down 4.7 grams. Potassium chemical symbol is K. Excuse me, little to no thought. The unit for grams is going to go on the bottom because that's what we're trying to get rid of. Now I pick my head up and look, what's my destination? Where am I trying to go? And it is asking about moles. So that's going to be my unit on the top, moles potassium. Now we need to think about our new equality. So our new equality, remember, was 1 mole equals X number of grams. Okay. So in this case, we've got to determine what is that X. To determine that, you're going to need to look at a periodic table. So I find potassium on my periodic table. I look at the number on the very bottom, and I see that the molar mass of potassium is 39.098. Okay. So that is the equality that is applicable to this problem because we're talking about potassium. So now that we have the values for our equality, we notice the number 1 is still attached to mole. It's going to be that way for a while. And then the number 39.098 is attached to grams. So units of grams cancel. We're going to be left with the unit of mole. And just like before, we multiply across the top, divide by the bottom. 4.7 times 1 divided by 39.098. And we get, this is what my calculator spits out. Okay. Again, we've got to consider significant figures. So where do we look for that? And we always look in this first quadrant here. So we're limited to 2 sig figs. So the answer that I would report is 0.12 moles of potassium. That would be the correct answer. Here's a graphic from your textbook, just helping you with deciding the setup. So we're starting in atoms, we're going to moles, and then just that reminder that we're dividing by molar mass. We actually don't need this piece, not something we'd have to remember because we're going to let the units guide our problem. So the units will set up that problem for us. But if you find that helpful, you can go ahead and use that in your example. Okay. Let's look at one more example going the other way. So a liter of air contains 9.2 times 10 to the negative 4th moles of argon. What is the mass of argon in a liter of air? So go ahead and pause the video, see if you can figure it out. Then I will join you and show you how I do it. All right, so unit conversion, we're going to start the same way we start every unit conversion. We're going to write down the information that's given. So 9.2 times 10 to the negative fourth. We have moles of argon. Little to no thought, moles of argon are going to go in the bottom quadrant because that's what we're getting rid of. We're dividing by it, cancels out the unit. Pick my head up and look. What is my destination? What is it asking for? What is the mass? So mass is always going to be grams. So we're looking for the grams of argon. So how do we determine what numbers to put in here? So we have to think about our new equality. 1 mole equals X grams. How do we determine that X? Well, our problem's asking about argon. So we go to a periodic table, we find argon, we look at the number on the very bottom, and the molar mass of argon is 39.948. 39.948. Okay. Now we're ready to plug those numbers into our problem. So the number 1 is attached to mole, so that's going to go on the bottom. And the number 39.948 is attached to grams. Multiply across the top, divide by the bottom. So we're going to have 9.2 times 10 to the negative fourth times 39.948 divided by 1. And my calculator spits out this. We've got to consider sig figs, right? So we always look at the first quadrant to determine the number of sig figs. So we're limited to 2 sig figs. So I can report 0.037, and that is grams of argon. I hope you guys found this helpful.